Last week we finished up chapters 1 and 8, which dealt mainly with measurement and conversion problems, doing calculations using both the metric and the English system. So we hadn't really got into much chemistry yet, and that's going to change now. If you were tired of math, well, then you're in for a break, because the next 8 chapters have very little math in them. They're mostly concepts about chemistry. We're going to start at the beginning, assuming you know nothing. And so we're going to start back in ancient Greece at about 500 BC, when the Greek philosophers first began to wonder what the nature of matter was. And we're going to work our way through the development of chemistry all the way up to the 1920s and 30s, when they came up with the concept of quantum mechanics to explain the nature of atoms and the universe, for that matter. So we'll start out by sort of having a historical view. We're going to go through a timeline. I really like the history of chemistry, and so I have the time on these videos to do that, so I'm going to take you through all the different people and the discoveries that they made. I hate it when someone just gives me a fact and they can't support it. So my teaching philosophy has always been, if I'm going to tell you a scientific fact or a theory, I want to be able to give you the experimental evidence to support that. So we'll be doing that as we work our way through chapter 2. And so chapter 2 is sort of an introduction to chemistry. And then in chapter 11, we're going to get into much more detail. By the time we finish chapter 2, you'll have a basic idea of the structure of an atom. And then in chapter 11, we're going to get into more detail about the actual structure of the atom and how that determines the chemical and physical properties of the various elements. So I've got the videos are uploaded on Canvas for chapter 2, so go ahead and take a look at those, and then if you have any questions, of course, you can always reach out to me. In the first 2 chapters this semester, we dealt mainly with measurement and conversion problems, learned about the metric system and how we could relate that to the English or American system, but we didn't really get into actual chemistry. So we're going to change that in chapter 2. We're going to talk about what chemistry is and what things are actually made of. What is the nature of the material that chemists deal with? So what is chemistry actually? There is a fairly simple definition. It's just the study of matter, which we'll talk about that in a moment, and its changes. Basically, chemists are interested in doing 2 things. We want to understand the nature of the matter in the universe and figure out how we can change it into other and hopefully more useful types of materials. What is matter then? Very simple, anything that has mass and volume. So if you can measure it like that, if you can feel it, if it's tangible, then that's an example of matter. I'm sure you've heard of the 3 states of matter. There are actually 7, believe it or not, but there's only 3 that we commonly deal with, and that, of course, is gas, liquid, and solid. In gases, the particles are fairly far apart. In liquids and solids, they're very close together. What is it that determines then whether something is a gas or a liquid or a solid at room temperature? Why is it then that some substances are solid, some are liquid, and others are gases at a given temperature, like room temperature? The answer is something called intermolecular forces. These are attractive forces or attractions that exist between all substances. Every material has intermolecular forces. We'll learn later in the semester what the nature of those is, where they come from. But at this point, you just don't have enough of a background for me to be able to get into much more detail, but that will come later. In a gas, such as oxygen, these attractions are weak. When the oxygen molecules bump into one another, they can't quite stick together because the bond isn't strong enough, and so they simply bounce off, and that's why oxygen is a gas. In a liquid like water, where the attractions are moderate in strength, they're powerful enough to keep the water molecules together, but they still have enough flexibility that they can move around freely. That's why liquids are able to flow. In a solid, the attractions are very strong,
And they're strong enough that not only are the particles stuck together, but they're locked in a rigid arrangement, like, say, a crystal of salt, or, as in our objectives, a piece of gold. This is oxygen at room temperature. There are attractions between the oxygen molecules, but they're simply not strong enough to hold them together. Is it possible for oxygen to exist as a liquid or a solid? The answer is yes. That's for most substances. They can exist in any of those three states depending on the temperature. If we cool our oxygen down to minus 183 degrees Celsius, the attractions are still the same. They haven't changed, but the molecules are moving much slower, so when they bump into one another, those attractions are strong enough to hold them together. They simply don't bounce off of each other because they don't have enough kinetic energy to do that. If we lower the temperature even further to minus 219 degrees Celsius, now the attractions between the molecules are enough to actually lock them into a solid state. Again, the attractions haven't changed. It's just that the molecules of oxygen are now moving very slowly. As long as people have existed, they've been curious about the nature of the universe. So since chemistry is the study of matter, we're going to take sort of a historical tour of how people decided what the nature of matter was. And we'll begin back in ancient Greece. A Greek philosopher by the name of Democritus first came up with the idea that matter consisted of tiny particles, which he called atomos, which meant indivisible. Now, the story goes, the way Democritus came up with this idea is he was looking at a beach one day, and from a distance, it looked like the beach was made of smooth, continuous material. You couldn't see that there were individual particles. But when you look at sand up close, you realize, it's actually made of a whole bunch of little individual particles. And he wondered that perhaps everything was that way. Maybe a piece of gold, if you divided it down small enough, you would end up with indivisible little particles of gold. Aristotle, of course, a very famous philosopher from ancient Greece, he had a different idea. He thought that matter was continuous. He thought that if you divided a piece of gold down smaller and smaller, there would be no limit to how tiny it could become. Now, Aristotle, of course, was a very renowned philosopher, so his ideas held sway, and for the next 2,000 years, the atomic concept of matter was pretty much lost. People simply thought, well, Aristotle, he was a bright guy, we'll just believe what he said. Now, keep in mind that neither Aristotle nor Democritus did any experiments to support their hypotheses. That really wasn't something the Greeks did. They philosophized, they discussed and debated, and when they came up with an idea that seemed reasonable, that became the facts. That was before people started using the scientific method and requiring experimental data to support their ideas. A couple of thousand years later, in the 1700s, we get to what I like to call the age of experimentation, where chemists actually began, doing careful experiments and measuring the things they were doing. Back in those days, chemists didn't have all the fancy tools and equipment that we have these days. But one thing they did have were very good balances. They could weigh things very accurately. People needed good balances. If you were dealing with precious commodities like precious metals, or even in those days, things like pepper were so incredibly expensive, you had to be able to weigh tiny amounts of things very accurately. And so chemists began to measure the masses of materials involved in various chemical reactions. Let's take, for example, this reaction between oxygen and hydrogen. If we take 8 grams of oxygen and 1 gram of hydrogen, what will we get? Well, we're going to get 9 grams of water. And chemists noticed that anytime they did a chemical reaction, if they weighed the materials that they put into the reaction, and they weighed the amount of product that they got from the reaction, it was always the same. And that led to one of our first major laws of chemistry, which is called the law of conservation of matter, or sometimes called the law of conservation of mass. Antoine Lavoisier was a very famous chemist in the second half of the 1700s in France. We sometimes can simplify this. We can say that matter can neither be created nor destroyed in a chemical reaction, or very simply, what goes in must come out. You can't create material in a chemical reaction. It can't simply disappear. And of course, chemists didn't really understand at the time why that was the case. That would come a little bit later. Let's take a look at a second reaction, but this time we're going to increase our oxygen to 9 grams, but keep the 1 gram of hydrogen. How much water are we going to get in this reaction? You're probably thinking 10 grams to follow the law of conservation of mass, but unfortunately that's not correct. You're still going to get 9 grams of water. Now this looks like a violation of the law of conservation of mass, but it's not exactly, because in addition to the 9 grams of water, there's going to be 1 gram of oxygen left over. For some reason, the oxygen and hydrogen only wanted to combine in this very specific ratio of 8:1. They didn't want to combine in a ratio of 9:1. We could do a similar reaction, but this time we'll increase the hydrogen by 1 gram. And not surprisingly, we're going to get 9 grams of water again. The 8 grams of oxygen will combine with 1 gram of hydrogen to give us 9 grams of water, and we will end up with a leftover gram of hydrogen this time. These observations that elements always seem to want to combine with each other in a very specific ratio gave rise to our second law, which was called the law of definite proportions, which was proposed by a chemist, Joseph Proust. And the law of definite proportions simply says that a given chemical compound will always contain the same proportions or ratios of elements. Water is always 8 parts oxygen to 1 part hydrogen by weight. If you take a sample of water out of a well or a lake or anywhere and you break it apart, if you take 9 grams of water, it will always produce 8 grams of oxygen and 1 gram of hydrogen. Again, chemists weren't entirely sure at the time why this was. That would be coming up fairly soon. This law can also be called the law of constant composition. So constant composition, definite proportions, basically means the same thing. Now let's take a look at another reaction. This time I'm going to double the oxygen to 16 grams. So we have 16 grams of oxygen and 1 gram of hydrogen. And what are we going to get? It's not 9 grams of water. This time we're going to get 17 grams of a different compound, hydrogen peroxide. It turns out that it's possible to make more than one compound from the same elements. If you combine hydrogen and oxygen in an 8:1 ratio, you get water. If you double the oxygen to a 16:1 ratio, you get hydrogen peroxide. And this led us to our third very important law, which was called the law of multiple proportions. And essentially what the law of multiple proportions says is it's possible to make more than one compound from the same elements. If we couldn't do that, there would not be very many chemical compounds. Carbon and hydrogen make millions of different compounds with different proportions, but each individual compound will obey the law of definite proportions. Hydrogen peroxide is always a 16:1 ratio. Water is always an 8:1 ratio. So how did chemists make sense out of all of these experiments and observations? If you remember back in ancient Greece, there were two competing ideas. Democritus believed that substances consisted of individual particles, and Aristotle thought that matter was continuous and could be divided into infinitely smaller pieces. For example, let's take a look at a paint palette. Now, the paint is a continuous type of thing. If we mixed together red and blue paint, how many different shades of purple could we make? And essentially, it would be infinite. You could take a tiny speck of blue and the whole glob of red, or vice versa, or anything in between. If elements were continuous, like the paint, how many different combinations of, say, hydrogen and oxygen would be possible? It would essentially be infinite. Now, that's not what chemists found. They found that it was actually a very limited number. In fact, hydrogen and oxygen only make two compounds, water and hydrogen peroxide. Suppose then that matter were made of discrete objects, for example, like a key and a lock. How many keys can you put into a lock at one time? It's just one. You can put one key in one lock. You can't put 1.5 keys or 2.735 keys. A key is an indivisible object. You can have one key and one lock. So chemists began to wonder that maybe they could explain these observations if Democritus were correct and matter were indeed discrete particles. As another example, let's consider the marking pens that we use in class. Suppose the marking pen weighs 8 grams and the cap weighs 1 gram, sort of like our oxygen and hydrogen we looked at in our hypothetical example a minute ago. It's easy to see that you could combine 1 gram of cap with 8 grams of pen, and that would give us 9 grams of marking pen. Works out perfectly. Now suppose, on the other hand, I wanted to combine 12 grams of marking pen with this 1 gram of cap. If I were to do that, I would need 1.5 marking pens. I can get 8 grams of marking pen from my 1 pen. I can get my 1 gram of cap, but if I wanted 12 grams of pen, I would need another 4 grams. I would have to slice this pen in half, and you can't do that. If you cut that pen in half, you'll just have a mess. Many things in life are discrete objects. You can't go to the store and buy half an egg. You can't have half of a key to open a lock. So it's not possible to get 4 grams of marking pen. It's 8 or nothing. At least it seems that way at the moment. However, what if we decided that we wanted 16 grams of marking pen? Would that be possible? Could we have 16 grams of pen and 1 gram of cap? And the answer is yes, that would be possible, because now we have 2 complete and indivisible marking pens. This is sort of like our hydrogen peroxide example. When we doubled the grams of oxygen, that worked out okay, because now we have 16 grams, which is 2 pens, and 1 gram, which is 1 cap. Theoretically, we could have 24 grams of pen, or we could have 2 grams of cap. Not all of those exist. As you're going to learn in upcoming chapters, even though a combination of atoms is possible, they don't all exist. There are other considerations in terms of how atoms want to bond with each other. But when they do bond, they're always going to be bonding in these whole number ways. You can't simply cut an atom in half any more than you can cut a marking pen in half. In the early 1800s, John Dalton, the person who came up with the law of multiple proportions, sort of put all of this together. He looked at the work that other chemists had done and work he had done himself, and he came up with the conclusion that the only good explanation for all of these observations is that Democritus was right, and elements actually consisted of these tiny particles which he called atoms. So these are the key points of Dalton's atomic theory. Most importantly, of course, is he decided that matter consists of indivisible particles, and he called them atoms after Democritus' term atomos, which meant indivisible. He also concluded that atoms of the same element are identical, but they're different from atoms of other elements. So all atoms of gold are exactly the same. All atoms of hydrogen are the same. Sort of like Legos you might have in a Lego kit. You've got all the different types of pieces that you can put together. Atoms, of course, cannot be created or destroyed. That's where the law of conservation of mass comes in. That's the reason that whatever amount of mass you put into a chemical reaction, you get the same amount out. Atoms can't be destroyed in the reaction, and you can't simply create new ones out of nothing. And he also concluded that atoms of different elements are what come together to make compounds. And he found that they, for the most part at least, came together in simple whole number ratios. They didn't really know a lot of chemical formulas back in Dalton's time, but they knew a lot. For example, water was always 2 atoms of H and 1 atom of O. Carbon dioxide was always 1 atom of C and 2 atoms of O. Now, it turns out that there were a couple of things in Dalton's theory that ended up not being entirely true. Can you think of anything in this theory that we know now is not completely true? Well, the first one is indivisible. We know now, of course, that atoms can be broken down. That's what happens in nuclear processes. But we can't really fault Dalton. I mean, back in those days, no one knew about nuclear processes. That was almost 100 years in the future. The other thing that they found out later is that not all atoms of an element are exactly the same. They are very, very similar. There are actually 2 different kinds of gold atoms, and they're almost indistinguishable. If you had a bar of gold made out of each of the 2 different types of atoms, it would be extremely difficult to tell them apart. So they simply didn't have the equipment back in Dalton's time to be able to differentiate those. So we can't really blame him. These assumptions were very logical at the time. Now, at about the same time period as Dalton was doing his atomic theory, an Italian physicist discovered how to produce something that we completely depend on in modern life. Any idea what is it that he figured out how to make that we would not likely survive, or at least not survive well, without? Well, I'll give you a hint. His name was Alessandro Volta. And of course, the volt in Volta probably tells you that it was electricity. Before Volta came along, no one really knew how to make electricity, in a readily available form. They had static electricity. You could rub things together and make sparks, but nobody knew how to produce electricity in a consistent fashion. And Volta figured out how to do that. This is one of his early batteries here. It's basically just copper and zinc metal separated by little pieces of fabric or cloth that have been soaked in salt water. This is basically what we call a voltaic cell, named after Volta. It's got a piece of zinc, a piece of copper, and then a porous material between. It can be cloth, it could be paper. You soak it with something like salt water so that it will conduct electricity. And a zinc copper cell will produce about 1 volt of electricity. Not a lot. But what Volta did is he started stacking these things together. They put hundreds and thousands of these things together in laboratories to make a lot of electricity. So this is what we refer to as a battery. Now, these guys here, believe it or not, although it says battery right on the label of all of them, they're not actually batteries. That's one of the things that annoys me, because they're not true batteries. A battery, you may have heard that term before, if you've ever heard of an artillery battery. An artillery battery is a group of artillery pieces, like a row of cannons. If you've ever taken a battery of tests, like you might do for a medical diagnosis, a battery simply means a group of something. So this is actually a battery because it consists of more than one cell linked together. Now, a car battery is an actual battery. A car battery contains 6 cells, Each of those cells produces 2 volts of electricity, and that's a total of 12 volts. That's the way they refer to car batteries, as a 12-volt battery. Different chemicals produce different amounts of voltage. In the old voltaic cell, zinc and copper produce about 1 volt. In these Energizer type of batteries, you get 1.5 volts between zinc and manganese. A car battery uses lead, and the lead cells happen to produce 2 volts. Now, a 9-volt battery is an actual battery. It has the same chemicals that are in the AAA, AA, C, and D cells, but there are 6 of those stacked on top of each other. So 6 1.5-volt cells give us our 9 volts. Over time, people have just gotten lazy. Even the companies that make these, I guess they decided it was too confusing for your average person. No one wanted to call these things cells and these things batteries, so they just said, heck, let's call everything a battery. But I'm a purist, so that's a cell, that's a battery. Another kind of battery is called the potato battery. Some of you may have seen the potato clock before. They're pretty cool. You can buy these things on Amazon or in various stores. And the potato basically acts as that bit of salt water soaked cloth. The liquid inside the potato is conductive to electricity. So there's 2 pieces of copper and 2 pieces of zinc. It's essentially 2 cells linked together. So this 2 potato clock will produce about 2 volts of electricity, and it's enough to power one of these nice little liquid crystal clocks. They don't take a lot of electricity. You could theoretically hook hundreds of potatoes together and make an awful lot of electricity, but that would be a waste of many perfectly good potatoes. Of course, scientists were trying to figure out where this electrical fluid, as they called it, came from. Well, in the voltaic cell, it's clearly coming from the piece of zinc. They knew that this electricity or electrical fluid flowed from the piece of zinc to the piece of copper. What's the piece of zinc made of? The answer, of course, it's made of atoms. Dalton had just told us that at about this same time. So the atoms, Dalton had thought that atoms were indivisible little balls, but apparently this electrical fluid must be part of atoms, so the logical conclusion was atoms aren't indivisible after all, because they contain at least one other material, which is this electrical fluid. This electrical fluid could leave the piece of zinc, something was left behind, and the electrical fluid had left. So what is this electrical fluid? During the course of the 1800s, scientists studied electricity and tried to figure out what its nature was. And they had 2 basic ideas. Some people thought that electricity was some kind of wave. Light was a wave, and so they, well, maybe electricity is a wave as well. It's a wave of energy flowing through a wire. Others thought that perhaps an electron was some type of particle. And so they did a lot of experiments during the course of the 1800s to try to determine, is the electron a wave or is it a particle? In 1870, William Crookes invented this device here, which is called a Crookes tube, or in generic terms, it's a cathode ray tube. You may have heard of a cathode ray tube before, or a CRT. If you still have an old-fashioned television, one of the big bulky ones, that picture tube in the television was a cathode ray tube. It simply was wider at the front and narrower at the back. So scientists used this cathode ray tube to try to determine the nature of electrical fluid. They could fire a beam of this electrical fluid down this tube, and they experimented with this, trying to determine what's the nature of this material. Let's take a break for a moment and head on over into the lab. I have some Crookes tubes in the laboratory, and let's do some experiments ourselves and see if we can figure out what the nature of electricity actually is.
These are a couple of cathode ray tubes very similar to what William Crookes used. In fact, he used one an awful lot like this one, and we'll take a close-up view of it in a moment. It may be a little difficult for you to see from here, but there's a little paddle wheel inside this tube that can move back and forth, and we're going to take a look at that. We'll zoom in on that much more closely in a moment. So inside this glass tube is mostly a vacuum. That allows the electricity to travel freely from one end of the tube to the other without running into any molecules of oxygen or nitrogen. We hook it up to a power supply. I've got a transformer here that puts out many tens of thousands of volts of electricity. So you can hear the power when I turn it on. Listen to that buzzing sound there. It's putting out quite a bit of electricity. And we're going to use that to try to determine the nature of electrons. So once Crookes invented this tube back in 1870, scientists used it to try to determine the nature of an electron. We'll be talking in a lecture on the video about J.J. Thomson, who used this to pin down the nature of the electron. As I said in the video, at the time there were two different opposing theories. Some people thought electrons were waves, and some thought they were particles. Now this tube is a pretty handy way to illustrate that. If electrons were a wave, then imagine what would happen if you shined a light on a little paddle wheel. Imagine those windmills out on the delta. If sunlight hits those windmills, do the waves of light make those turbines spin? Of course not. What is it that actually makes those huge turbines spin around and make electricity? The answer is, of course, it's the particles in the air, the oxygen and nitrogen molecules physically hitting those paddles on the blade and causing them to turn. Now, if the electron is a wave, we would expect it to have no effect on our little paddle wheel. But if the electron were a stream of particles, then as those particles hit that little wheel, they should make it move. So let's see what happens. Let's turn on the power here. And we'll do a zoomed in version of this in a moment, but let's turn this up. Maybe you can see, I turn the power up, the little paddle wheel starts moving from one end of the tube to the other. It's rolling along, pushed by a stream of electrons. I can reverse the polarity, switch the positive and negative, and now I can make the wheel go back the other direction. And I can keep doing that back and forth if I wish. So based on this, it appears like the electron is, or the electricity, or this electrical fluid that they used to call it in the 1800s, was indeed some kind of particle. At least that's what they thought in 1897. Things changed in the next 30 years. So we'll get to that a little bit later. So why don't we move in and see if we can get a little more close-up view of our Crookes tube. Let's go ahead now and take a closer look at that little paddle wheel. So you can see the paddle wheel here. It's on a little glass track, so it's free to move back and forth. We have our power connected to the two terminals on either side. So let's turn on the power. And now we'll turn up the voltage, and there goes the paddle wheel, pushed by the electrons to the other end of the tube. If I reverse the polarity, I can make it go in the other direction. Now I can make it go faster if I turn the voltage up. If I turn the voltage up, you'll see that little wheel goes very quickly, because at a higher voltage the electrons have more kinetic energy. They are essentially moving faster. So it was observations like this that allowed scientists to determine that the electricity or electrical fluid was apparently some type of particle. As you'll see in the video, in 1897, J.J. Thomson managed to definitively identify the electron, even determining the mass of the electron, which turns out to be very, very tiny. Well, apparently the electron is a particle, based on our experiments. At least it is for now. It turns out that the answer is a little more complicated than we thought, but that's still about 20 years in the future. So let's sort of summarize where we're at right now. So here we are in 1897, and J.J. Thomson has
identified the electron. He's determined it's a particle and gives it the symbol of E with a negative sign since it's got a negative charge. He's able to determine the mass of the electron using the cathode ray tube and finds that it's extremely light. It only weighs 9.1 times 10 to the minus 28th grams. That's about 1,000th of a trillionth of a trillionth of a gram. That is not much. So here's my next question for you. Are atoms neutral or are they electrically charged? I think we should do an experiment. So let's take a break again for a moment and let's do another experiment and figure out whether atoms are indeed neutral or electrically charged. You think about that, what you think the answer is, and let's go into the lab and test it.
Now let's do an experiment and try to figure out if atoms are actually neutral or are they electrically charged. Now, what's the most important thing we're going to need to do the experiment? The answer, of course, is we need atoms. I suppose I could go into the stockroom and ask Trini for a bottle of atoms, but that's really not necessary, is it? Because atoms are everywhere. The wall, the door, the floor, the camera that's filming me, they're all made of atoms. So, just for the heck of it, let's use the tabletop. That will be our source of atoms. So before we do the experiment, I want you guys to ask yourselves, are atoms electrically charged or are they neutral? Let's test it. Now, don't do this at home, ladies and gentlemen, because it could be very dangerous, but I am going to take the risk here just to show you whether atoms are electrically charged or neutral. The easiest way to tell would be to touch some atoms. Now, if I touch the atoms in that tabletop and I get blasted across the room, we know they're electrically charged. But if I survive, then we know atoms are neutral. So let's very carefully test this. So I'm going to put my finger down on the tabletop. Oh my God. I didn't get blasted across the room. Not surprisingly, of course, atoms are neutral. If atoms were electrically charged, then we would be getting zapped all the time. Every time we touched anything, we would get an electrical shock. So atoms are indeed neutral. Now we know that atoms contain a negative charge from the electrons, and therefore the only way that atoms can be neutral is there has to be something positive in the atom to balance that out. So that's what chemists went to look for next.
We now know two important things about atoms. One, we know that they contain this negative particle, which we've called the electron, and we also know that there's some kind of positive material in the atom to balance out those charges. Scientists began to wonder what might the atom actually look like. And so they came up with various ideas or various theories about what the structure of an atom might be. J.J. Thomson, the person who discovered the electron, came up with something which is called the plum pudding model of the atom. And he thought the atom might look something like plum pudding. Okay? This is sort of his model of plum pudding. There's this large cloud of positive charge. That's our pudding. It's just this big diffuse blob. And then the electrons are like negatively charged little plums stuck on the surface. This was a perfectly good hypothesis. They hadn't discovered protons yet, so the idea that the positive part of the atom was just one big ball of positive charge was perfectly fine. Now, of course, if you're going to come up with a model or a theory, you have to be able to test it. And so his colleague, Ernest Rutherford, came up with an experiment which is called the gold foil experiment. In the gold foil experiment, their idea was to fire subatomic particles through a piece of gold foil, which was supposedly made of these plum pudding atoms. Now, if the positive part of the atom, where most of the mass resided, was spread out over the entire atom, it would be very diffuse. It'd have a very low density. These particles that they were firing through the atom were extremely dense and had a very high kinetic energy. So in theory, those particles should be able to just blast through that gold foil like they weren't there. So they decided to set up an experiment where they fired these particles through a piece of gold foil, and according to the theory, every single particle should go shooting straight through the foil like it wasn't there. Every particle should go right to the other side and be detected. And over 99.99% of the particles did exactly that. But what about that 0.01%? A lesser scientist might have said, well, that's just experimental error, and not worried about it. But Rutherford was a good scientist. He wasn't willing to settle for being 99.99% right. He wanted to be able to account for 100% of the experimental data. So he tried to figure out what could the atom look like such that almost every particle passes through the gold foil, but a very tiny percentage don't. And based on those results, he came up with a new model of the atom. His new model of the atom is called the nuclear model because it contains a nucleus. He envisioned that all of the positive part of the atom was squeezed into a tiny little speck in the center of the atom. So almost all of the mass of the atom is in that tiny little nucleus. Around the nucleus, we have our electrons. And between the electrons and the nucleus, there's nothing but empty space. So it's very easy for most of those radioactive particles to pass through the atom completely unaffected because they're literally passing through nothing. But this incredibly dense nucleus, this nucleus is so dense it's virtually the same as a black hole. It's that dense. So when the alpha particles hit that nucleus, they would simply bounce off. If they hit it at an edge, they would simply be deflected at an angle. Some of them hit it head on and bounced right back. So his nuclear model of the atom did a pretty nice job of explaining the behavior of the atom. So in 1911, we now have this new model of the atom, and it's the model that we still use, that the positive part of the atom, they didn't know what those were yet, but the positive part of the atom was in a tiny little dense speck in the center, and the electrons simply were flying around the outside. All right, let's summarize again what we know about atoms at this point. So in 1897, we found that atoms contain these negative particles called electrons. By 1914, they had determined that this positive part of the atom was actually another particle called the proton. And the proton is, although a very light particle, it weighs about 1/trillionth of a gram, it was still about 2,000 times heavier than an electron. So the electron is extremely light. It's sort of like a fly landing on a baseball. The proton is much, much heavier than the electron. This is basically our Rutherford model of the atom then. We have our nucleus with the protons in the center. The electrons are flying around the outside, and we have all that empty space in between. How could we figure out the mass of an atom? If we knew how many protons and electrons were in an atom, couldn't we simply add up the masses of the protons and electrons to determine that? Yeah, that should work, absolutely. The problem we have at this point, however, is the gram is not a very convenient unit for weighing something as tiny as an electron and a proton. For example, if any of you have young children, if you brought your baby to the pediatrician and they told you how many tons the baby had gained in the last month, or how many miles they had grown, that wouldn't work very well because that wouldn't be a convenient unit. Weighing electrons and protons in grams is not very convenient because these guys are very, very tiny. So scientists needed a smaller unit. And they could have used milligrams or nanograms or femtograms even, which is a quadrillionth of a gram, but none of those units were tiny enough. So they did what people have done since the dawn of time, and that's invent a new unit. They said, you know what, we need a unit that is so tiny that it would be convenient to work with protons and electrons, and they created a new unit called an atomic mass unit. When you invent a unit, of course, you get to decide what its value is, and they set the atomic mass unit equal to 1.67 times 10 to the minus 24th grams. Obviously a very good choice because that's the same as the mass of a proton, which means now a proton weighs a nice round 1 AMU. An electron then weighs about 1/2000th of an AMU. Let's take a look then at a hydrogen atom. This 1 up here at the top is the atomic number of the atom. It's the number of protons in the atom. Now at this point, the atomic number also tells us the number of electrons in the atom. We've just decided a little while ago that atoms are neutral, at least for the time being. And so the number of protons and electrons is going to be the same. So if we wanted to figure out the mass of this atom of hydrogen, we'd simply add the mass of a proton and the mass of an electron together. This number at the bottom of the symbol is the atomic mass. This is what an atom of hydrogen actually weighs, just slightly more than 1 AMU. So let's see if our calculation matches reality. 1 proton plus 1 electron, if we add these together, is 1.005 AMUs. That is almost exactly what we predict, so that worked out pretty darn good. Of course, we never like to be satisfied with simply one result, so let's do this again, but this time we'll take a look at helium. So helium has 2 protons and 2 electrons, and its atomic mass is just about exactly 4 AMUs. If we add up the 2 protons and the 2 electrons that helium atoms contain, oh my lord, it only comes out to be 2 AMUs. It's only about half as much as a helium atom actually weighs. So of course, what did scientists immediately conclude? There's got to be something else in the atom. We're missing something. Now the good thing is we clearly know something about the properties of this missing object or missing item, and that is it has to be neutral. We know that atoms are neutral, and we know they contain equal numbers of protons and electrons, so this third component of the atom must be neutral. And that's why it was harder to find. Protons and electrons could be passed down a cathode ray tube, they could be deflected by magnets and studied very nicely, but a neutral particle is going to be unaffected by those things. But eventually, in 1932, they discovered the neutron. Turns out that the mass of a neutron is just about the same as the mass of a proton. So if we added 2 neutrons to our helium atom, now it adds up to almost exactly the atomic mass. Now this number is not going to be exactly the same. There are some other factors at work here that you guys aren't familiar with. When protons and electrons and neutrons come together and form an atom, their masses change slightly for reasons that we can get into at a later time. What exactly is the function of the protons, neutrons, and electrons? Each of them has a job to do in the atom. To a chemist, the most important part of the atom is the electrons because the electrons are on the outside of the atom. The electrons determine the chemical properties of an element. Because they're on the outside, when 2 atoms collide with each other, it's the electrons that are interacting with one another. So I think I've said this before and I'll say it again, unlike what your parents tried to teach you when you were kids, that it's what's on the inside that counts, when it comes to an atom, that's unfortunately not the case. It's what's the outside that counts, it's how they look. So chemistry is basically involving the study of electrons. In chapter 4, the next chapter we're going to get into, we're going to be studying nothing but the electrons. We're going to find out everything we can about how the electrons behave in the atom, and we'll be able to then predict what atoms are going to do. The protons also have a very important job, not as glamorous, of course. Their job is to keep the electrons from flying off into space. Packing a bunch of negative particles close together in a tiny little space is a recipe for disaster. Those electrons want to fly off into space. It's the job of the protons to keep those electrons close into the atom. The neutron has a similar function. The job of the neutron is to keep the protons together in the nucleus. That's even more difficult because the protons are packed right next to each other. At least the electrons are flying around with some space between them. Keeping those protons in the nucleus takes a massive amount of force. Chemical energy, the energy you get from burning gasoline or setting off an explosive, that energy is stored in the electrons in the atom. Nuclear energy is stored in the nucleus, in the protons and the neutrons. Because the forces are so much greater, they're perhaps 1,000,000 times greater in the nucleus to hold those protons together, nuclear energy is about 1,000,000 times more powerful than chemical energy. Isotopes are another exception to Dalton's atomic theory. Dalton said that all atoms of a given element are identical, and I mentioned earlier that you can have more than one variety of a particular kind of atom. For example, these represent the 3 isotopes of hydrogen. Iso means the same, so isotopes, what it means is they have the same number of protons. You'll notice that each of these 3 hydrogen atoms has 1 proton. The number of protons is the one thing that defines an atom. The number of neutrons can vary. The number of electrons can vary. But the number of protons makes you what you are. Hydrogen is element number 1. It has 1 proton always. Helium is element number 2. It always has 2 protons. Uranium is element number 92. It always has 92 protons. But the neutrons can vary because that's not going to affect the balance of the charge. The simplest atom in the universe is this hydrogen atom here with 1 proton and 1 electron. Hydrogen is the one element that doesn't need neutrons because there's only 1 proton here. If you have more than 1 proton, you've got to have neutrons. Now we have this thing called a nuclear symbol that we use to represent an isotope. The subscripted 1 here is the atomic number. So the number to the lower left is the atomic number, which is the number of protons in the nucleus. In this case, it's 1. The superscripted number in the upper left is something we call the mass number. It is the number of protons and neutrons added together. And so 1 proton plus 0 neutrons, of course, that gives us a mass number of 1. In the second isotope, we have a proton and a neutron. So the atomic number, of course, is still 1, but now we have a total of 2 particles. 1 proton plus 1 neutron in the nucleus gives us a mass number of 2. And of course, in our third variation of hydrogen, we have 1 proton and 2 neutrons. So it has a mass number of 3. This is the symbol from the periodic table that you would find for copper. This number in the upper left-hand corner is the atomic number. That tells us that copper atoms have 29 protons, and at least to start with, they have 29 electrons. Pretty soon we're going to find that the electrons can change, but for now we'll assume that they are the same. This number below the symbol is called the atomic mass. It is how much the average atom of copper weighs. They take all the different isotopes of copper and they average them together and figure out what the average weight is, and that's what we report there. So where's the mass number? We've been talking about mass numbers, but apparently it's not on the periodic table. And the reason for that is very simple. Because atoms can have more than 1 mass number, it would be crowded to try to put those on the periodic table. For example, 1 isotope of copper has a mass number of 65, and the other isotope has a mass number of 63. So a copper 63 atom weighs about 63 AMUs, and a copper 65 atom weighs about 65. This average simply represents the average mass of the various atoms. You might be wondering why it's not 64. Why is it not right in the middle? And the answer to that's pretty simple. It's because there's more of these atoms than there are of these. There's about 75% of all copper atoms are the lighter version, and about 25% are the heavier. And so the average is going to fall somewhere in between. An atom like germanium has 23 different isotopes, which means 23 different mass numbers. It's simply too complicated or too crowded to put all of that information on there. Now, I'm going to tell you something I tell my students every semester. That atomic mass on the periodic table, ignore it. Do not use that number until we get to Chapter 9, and that's still quite a ways off in the future. If on the next quiz or exam number 1 you find yourself wanting to use that atomic mass, you're in trouble. You've already got the answer wrong, so I'm just going to give you a heads up. We will use the atomic masses, but that's going to come in a much later chapter when we start doing calculations involving the masses of elements and chemical compounds. I've mentioned on a number of occasions that atoms always start out with an equal number of protons and electrons, but that doesn't always remain the same. Most atoms are not happy, so to speak, or they're not stable with the number of electrons they begin with. And we're going to learn in the next chapter what number of electrons atoms actually need to have or want to have to become most stable. So atoms can either gain or lose electrons in order to reach this stability. For example, let's take a look at this iron atom. The fact that there's a positive 2 charge here tells us that this is an ion. Ions will always have either a positive or negative charge. You can think of an ion as an atom with a charge. So an atom itself will be neutral, but an ion will have a positive or negative charge. We know there's 26 protons because the atomic number is 26. The number of electrons, of course, must have started out at 26. But we now have a positive 2 charge. Well, how does an atom get a positive 2 charge? The answer is by losing electrons. If you think of it, if we have 26 pluses from our protons and 24 minuses from our electrons, that's an extra 2 positive charges. That's why this ion of iron has a positive 2 charge. So whenever an ion has a positive charge, that means it has lost electrons. We call a positive ion a cation. So a cation simply means that this is an ion with a positive charge. We can also have negative ions, and of course if an ion has a negative charge, that means that it has gained electrons. So in this arsenic or arsenide ion, we have 33 protons, of course, because that's what the atomic number tells us. The negative charge says, ooh, we have some extra electrons. If we've got 33 pluses from our protons and 36 minuses from our electrons, that's an extra 3 minuses, and that gives the arsenic its negative 3 charge, and we refer to negative ions as anions. And those two terms come from electrical terminology. The cathode is the positive terminal in a battery, and the anode is the negative terminal.
It's very common for my students to have trouble remembering how an atom gets a charge when it gains or loses electrons. People tend to think that losing something is a negative thing. And often they will say, oh, well, if it lost an electron, it must be negative. But that's not true, because losing an electron, since an electron has a negative charge, if you lose or subtract a negative, it's actually positive. 10 minus negative 1 is actually 11. So losing a negative makes you more positive. Now, the way you can remember this is I'm going to tell you my favorite chemistry joke. If we were in person all semester, you'd be hearing this joke a lot, because every time you forgot, I would tell the joke again. So you'll just have to replay it for yourselves. So here's the joke. Two atoms are walking down the street. First atom says, "I think I lost an electron." Second atom says, "Are you sure?" First atom says, "I'm positive." So now there will be lots of laughter. But the fact is, it's easy to remember that if you lose an electron, you become positive. If you gain an electron, you become negative. Think of an electron as like this marking pin. If I'm neutral right now, and I put a negative electron in my pocket, I've now become negative. So gaining an electron makes me negative. If I get rid of that electron, I lose that negative, I've now become more positive.
Most of you are probably familiar with the periodic table, but let's talk a little bit about how it came to be. A lot of people noticed that there were properties of elements that had similarities. Back in 1815, a chemist by the name of Dobereiner noticed that certain trios of elements had similar properties. For example, lithium, sodium, and potassium, or calcium, strontium, and barium. What he found was that if he arranged the elements in order of their atomic mass, so lithium the lightest, then sodium, and then potassium, that if you averaged the properties of the lightest and the heaviest member of the triad, the properties turned out to be very similar to that of the element in the middle. Now, interesting observation. Unfortunately, none of the rest of the chemistry folks seemed to think it was worth much, so nobody really jumped on his bandwagon there, and Dobereiner sort of faded into oblivion. It was quite a while then before someone else got brave enough to try to come up with some kind of relationship between the elements. So in the 1860s, John Newlands, a British chemist, came up with something called the law of octaves. He put the elements in order of atomic mass. Again, that's the one thing that everybody knew about even back in the 1800s. They didn't have atomic numbers, they didn't have mass numbers and such, but they did know what the relative masses or weights of the elements were. And he found that if he put the elements in order, that about every eighth element seemed to be a repeat of the first element, just like do, re, mi, fa, sol, la, ti, do. An interesting observation. And nobody seemed to care. No one really gave it any credence. And Newlands, for a number of years, was pretty much forgotten about. He did get his glory later on, but it took some time. But only a few years later, Mendeleev, a Russian chemist, came up with the first periodic table. You can see it looks quite a bit different than our modern periodic table, but he sort of put together the ideas of both Newlands and Dobereiner. He arranged the elements in order of increasing atomic mass, and like the law of octaves, he repeated his periods of elements every time he saw the properties repeating themselves again. So he would go across and then go back and start another row. This is, of course, what our periodic table looks like today. It's a little easier to recognize. Why do we call it a periodic table? What does the term periodic mean? It simply means that things are repeating periodically. The properties of elements repeat themselves on the periodic table. If all 118 elements had completely unique properties, that would make things very complicated. Fortunately, there's only a certain variety of properties that tend to repeat themselves. So because the properties are repeating on a periodic basis, that's why we call it the periodic table. If you've been to the library and you need a magazine or a newspaper, they send you to the periodicals section. Why do they call those publications periodicals? Because they're published periodically. Newsweek comes out once a week. The Stockton Record comes out once a day. The Reader's Digest once a month. They're all published on a regular, repeating, periodic basis. These vertical columns on the periodic table are known as groups, and the groups tend to have similar properties. We'll be doing an experiment this week where we're looking at the properties actually in the elements in group 2. This is the type of thing that Dobereiner noticed back in 1815. He saw that, for example, magnesium, calcium, and strontium had similar properties, and that calcium was sort of an average of the two. Going across horizontally, we have the periods. This was what Newlands did back in the early 1860s. He would go across through his elements, and he would notice the properties were slowly changing. The elements over on the left side are metals. They have the properties metals would have. They're shiny, they're malleable and ductile, they conduct electricity. And he found as you went across the table, the properties shifted to nonmetals. They become dull and brittle and became insulating rather than conducting. But then there would be a moment where all of a sudden the properties would instantly revert from completely nonmetal back to metal again. And that's why Newlands was arranging his elements in these octaves. Mendeleev did basically the same thing. So at this point, it seems like he's just done what those guys already did. But he went further. In 1869, there were about 50 known elements. So there was a lot of holes in the periodic table. For example, after zinc, the next known element was arsenic. Now, Mendeleev might have just gone zinc and put arsenic right next to it, but he didn't. And the reason he didn't do that is because he could see that the properties of arsenic were really nothing like aluminum and indium. Looking back to what Dobereiner did with his law of triads, we'd expect the element in the middle to be similar to the one above and below it. He did realize that arsenic was very similar to phosphorus and antimony, and therefore he put arsenic in between those. That's one thing he did. The next thing he did was he left empty boxes here and made predictions of what those elements would be like. He said, one of these days, someone's going to discover those missing elements, and here's what I predict their properties to be. He took the properties, say, of silicon and tin, averaged them together, predicted what germanium would be like. He did the same thing with aluminum and indium to predict the properties of gallium. And so it was those predictive properties of the table. That's why people accepted it. They looked and said, wow, this isn't just a list of the elements. This is actually a tool we could use. There could be an element that's unknown, yet we can predict ahead of time what its properties are going to be like. If we know the properties of, say, chlorine and bromine, we can probably make a guess of what the properties of iodine will be like. This little staircase that goes down through the table over on the right side divides the table between metals and nonmetals. You remember I mentioned a moment ago that on the left side we have metals and they slowly become nonmetals. This staircase is sort of the dividing line between those two. As you can see, most of the elements on the periodic table are metals. Only a small number of them are nonmetals. The nonmetals, though, are very important because living organisms are made almost entirely of a few of these nonmetals. So they are extremely important elements, even though there aren't as many of them as there are the metals.
Well, that wraps up everything for Chapter 2. So at the end of Chapter 2, we have basically determined that elements consist of atoms, and that atoms are made up of even smaller particles, protons, neutrons, and electrons. The protons and neutrons are in that tiny little nucleus at the center of the atom, and the electrons are flying around on the outside. We also talked a bit about the periodic table and how the properties of elements repeat, and we're going to be taking advantage of that when we get to Chapter 3. So next up, we'll be moving into Chapter 11, where we're going to delve into more detail into the nature of atoms. It's the electrons on the outside of the atom that are the key to predicting the properties of elements. And so we're going to spend all of Chapter 11 focusing on the details of how those electrons are organized.